Hello and welcome to the ENGR 320 Thermodynamics Recitation on Chapter 4. I'm Dr. Krishna Pakala and I'll be helping you solve some problems from Chapter 4 so that you can understand the lectures covered in this chapter. Let's do a quick recap of Chapter 4. So in this chapter we learned how to compute work in a moving boundary problem, and we are talking about closed systems in this chapter. And we learned that the work done can be different based on the type of process. It could be, for example, if you have a polytropic process, which is PV power n is a constant, then you have work done shown there. In general, work done is integral of P dV. So you could have an isothermal process, you can have a constant pressure process, which would be easier to compute for a constant pressure process. You can see that work done at the boundary is P naught, which is a constant pressure times the volumes at the initial and the final states. And we also learned the energy balance for closed systems. So E in minus E out is delta E system, which means that the net energy transfer either by heat, work, or mass will be equal to the change in internal kinetic potential energies. And in this course, we are primarily interested in the work done. Heat is something which we'll take it for granted in this chapter, in this course. However, you learn different forms of heat transfer in depth when you take a course on transport phenomena. And we also learned specific heats, which is one is the constant pressure specific heat and the specific heat at constant volume. For an ideal gas, we learned that the change in enthalpy will be Cp times delta T, and the change in internal energy will be Cv times delta T. Now let's look at some problems covering the topics which we just discussed. Let's look at problem 410 from your book. You're given a mass of 5 kg of saturated water vapor at 300 kilopascals is heated at constant pressure until the temperature reaches 200 Celsius. You're asked to calculate the work done by the steam during this process. So in any of these problems, it would be the best option to first identify the states in the system. For example, the initial state and the final state. So let me write what are all given for state 1. So we know that it is saturated water vapor. We are given a mass of 5 kilograms. Remember, it is a closed system, so nothing is coming in or going out of the system. We have a pressure of 300 kilopascals, and we know that for state 2, this pressure is constant, so it would be again 300 kilopascals. So we don't know yet what is the state of the fluid or the phase in state 2. However, we can quickly look at the tables and then determine that. First, let's determine what would be the temperature at this pressure. So the way we do that is, since we know that it's saturated water vapor, you go up to your saturation tables. In this case, since we are given a pressure, let's go to the pressure table, which would be A5 in your book. So the way we look up these guys is you go to your pressure which you're given, which is 300 kilopascals, and then look what is the saturation temperature, which is 133.52. So let me write that. So this is from table A5. Similarly, I can compute the specific volume at this state 1, and this would be equal to the Vg, since we are considering saturated water vapor. So again, if we were to go to table A5 and look at the pressure, we determine that Vg is 0.60582 cubic meter per kg. So let me write that, cubic meter per kg. So you see that state 1 is now completely determined by these two intensive properties, which is pressure and temperature. Now let's do what would be the state 2 phase. So for this, again, if you were to look up the pressure table, you see that the temperature which you are given at state 2, which was 200 degrees C, is greater than the Tsat which we found out earlier. So that would mean that we are in the superheated phase, so it would be superheated water. Okay, since T2 is greater than Tsat at the pressure of 300 kilopascals. And similarly, we can find the specific volume at state 2, which would be nothing but the specific volume of superheated water. And the way we determine that is go to your superheated tables, which are table A6 for SI units. So 300 kilopascals is zero point 0.3 pascals, megapascals. So look at the temperature, which is 200 degrees Celsius, and go up to the pressure, which is right here, and then you would see that the V is 0.71643 cubic meter per kg. So let me write that. And we determined this from table A6. Okay. So now we have enough information for us to now compute the work done by the steam. And whenever work done is by the system, then you should get a positive value by convention. Let's look at the process. So for a constant pressure process, work done by the boundaries would be P naught times V2 minus V1. In this case, P naught is your 300 kilopascals. It's a constant pressure process. So we know P naught, these are volumes, total volumes, but we know the specific volumes. So I can write the same equation as this. So if you substitute the numbers, 5 kilograms P naught and the specific volumes which we just computed, you should end up with work done is 165.9 kilojoules. And you see that the positive sign indicates that the work is done by the system. So if you were to represent this on a PV diagram, let's say this is at 300 kilopascals. So this would be your state 1 for a specific volume at V1, and then you're going to state 2. So the process would be represented like this. Okay, now let's move on to another problem. 425. 1 kg of water that is initially at 90 degrees C with a quality of 10% occupies a spring-loaded piston cylinder device such as shown in the figure which you can see from your book. This device is now heated until the pressure rises to 800 kilopascals and the temperature is 250 degrees centigrade. You are asked to determine the total work produced during this process in kilojoules. So again, the key here is to write the information we are given, and if we cannot determine the phase of a system, we should probably do it given couple of intensive parameters. So let's see what we are given at state 1. Again, the mass is 1 kg of water. You're given a temperature, which is 90 degrees C. You're given a quality at this state, which is zero point 0.1. And since you're given that a quality of 0 0.1, that means it would be saturated water. So if you go to the temperature table, since you're given temperature tables for saturated water, you can see that the corresponding saturation pressure from table A4 is 70.183 kilopascals. Table A4. Similarly, let's try to identify state 2. Given that the temperature is 250 degrees centigrade and the pressure has risen to 800 kilopascals, so now we have to identify the state at this system. Since we are given two intensive properties, we can determine the phase at this system. So you can do it a couple of ways. One is you're given the temperatures. So go to the temperature tables and let's go there. Okay, and then look at the saturation pressure. So if the saturation pressure right now here is 3976.2 kilopascals, which is greater than the pressure at P2, which is 800 kilopascals. That would mean that we are in the superheated zone. The easier way to look up this is you're also given a pressure of 800 kilopascals. So let's go to the pressure tables. In this case, it would be table A5. And then let's look up the temperature, which is the saturation temperature at 800 kilopascals. And you'd see that it is 170.41 degrees centigrade, which is less than T2, which would mean that we are in the superheated zone. So having known that, let us write that we are in the superheated zone. Okay. Now we can sense, and let me write here, since T2 is greater than Tsat. Okay. Now the specific volume would be determined from the superheat tables. So the pressure is 800 kilopascals or 0.8 megapascals. And you're given a temperature of 250 degrees centigrade. So go up across this line and then you'd end up with your V in meter cube per kg, which is 0.29321. And again, this is from table A6. So you can see that when we want to draw this on a PV diagram, even though we don't know exactly yet what is the specific volume at state 1, we can safely assume, since this is saturated, it would be less than the superheated specific volume. However, I know the pressures. You can see that it is 70.183 kilopascals at state 1, 800 kilopascals at state 2. So this is a linear increase. So the area under this curve, and I should probably multiply with this mass so that I'm talking about volume. So that would give us the work done. So the next step is to find V1. Okay. So we can easily compute V1 since we are given the quality at state 1. So V1 is Vf plus X Vfg. So you can determine Vf and Vfg, which is nothing but Vg minus Vf, from table A4 for saturation. So you would end up with 0.23686 cubic meter per kg. Okay. So now the work done, since this area is area under a trapezoid for a trapezoid, so we can compute the work done by taking the average of the pressures times the mass times the specific volume difference at state 2 and state 1 for a linear process. So I end up with 24.52 kilojoules. Again, the positive sign indicates that the work done is by the system. And let's say if you were not sure about this formula, you can easily arrive at this, since a couple of students talked about this in class. So the way you do that is you can divide the whole area into a triangle and a rectangle. Then the sum of these two areas will give you the total area under this linear process. So A1 plus A2, you go through the math here, you see that you end up with the formula which we had used before. Okay, now let's look at another interesting problem. So 429E. You're given a closed system which is shown in the figure, and it is operated in an adiabatic manner. So what is an adiabatic manner? There is no heat transfer. First, 15,000 pound force feet of work are done by this system. Then, work is applied to the steering device to raise the internal energy of the fluid by 10.28 British thermal units. You're asked to calculate the net increase in the internal energy of this system. So we learned that it is a closed system, and which would mean that there is no mass coming in, coming out. So that would mean that we can apply the first law of thermodynamics. So the general energy balance for any system undergoing any process we learned is E in minus E out is the change in the internal or potential or kinetic energies in the system. We have no contribution of change in kinetic or potential energy at this system, so there is only change in internal energy in the system, and we are not putting in any heat. It's an adiabatic process, so all we are doing is putting in work and getting work out. So this would be change in the total internal energy. We already given that the amount of work put in is 10.28 BTU, and you're given that the work out was 15,000 pound force times feet, and immediately you might jump in and take the difference, but see the units are different, so make sure you convert them, and you can either convert them to BTU or pound force feet, it doesn't matter, but make sure they're consistent. But generally we represent in British thermal units. So back of the book you can find that one British thermal unit is 778.169 pound force feet. So that would mean that this would be 15,000 over 778.169 BTU. So this is about 19.28 BTU. So now I can go ahead and compute the change in internal energy of the system, which would be 10.28 BTU, the work put in, minus the work delivered, which is 19.28 BTU. So that would give us approximately negative 9 BTU. Now let's look at another problem. 434 from your book. Saturated water vapor at 200 degrees centigrade is isothermally condensed to saturated liquid in a piston cylinder device. You're asked to calculate the heat transfer and the work done during this process in kilojoule per kg. So immediately you see that there is no information of mass given in the system, and you're asked to represent your answers in kilojoule per kg. That should immediately tell you that you're dealing with per unit mass type of problem. So you have to convert everything to per unit mass basis. Now let's first identify what are we given at state 1 and state 2. So state 1, you're given that it is saturated water vapor. You're given a temperature 200 degrees C. So I can compute a pressure at this. I know that since it is saturated water vapor, the quality is 1. So I can go ahead and compute V1 as well from the tables, which we will do pretty soon. And let me also write U1, and we'll talk about why I'm gonna do this. And since this is saturated water vapor, it will be equal to UG, internal energy per unit mass, and this would be equal to Vg. Okay. So since we are given temperature, let's go to the saturated tables and go to the temperature table. So for 200 degrees centigrade from table A4, I find that the pressure, which is saturation, is 1554.9 kilopascals. So this is 1554.9 kilopascals. Similarly, I can find Vg, which is given here, 0.12721 cubic meter per kg. And then I can find from the same table, I can find the internal energy per unit mass. So all of this I got from table A4. Okay. Now let's identify state 2. So this is condensed to saturated liquid now, and it is isothermal process, so it would be a constant temperature process going from state 1 to state 2. So that would mean that we have T2 200 degrees centigrade, and the saturation pressure we can determine again from the saturated tables, which would be exactly the same as found before. However, the quality now would be 0, and the specific volume at V2 will be Vf, which you can find from table A4, which is 0.00157 cubic meter per kg. And I can find U2, which will be equal to UF since it's saturated liquid, which is 850.46 kilojoule per kg. Okay. So we have enough information here to compute the work done and the heat transfer. Before we do that, let's quickly see how the TV diagram looks like for this process. If I were to plot the data on a TV diagram, you see that state 1 we have a saturated water vapor, and the quality here is 1, and then it's condensed to saturated liquid, so the quality is 0, and the horizontal line implies that this is an isothermal process, so this is how you would represent it on a TB diagram. Okay. Let's say if we want to represent this on a PV diagram. And even though we don't know the mass, let's say if I'm doing per unit mass and I'm going to multiply the same mass, I can see that it's a constant pressure process going from state 1 to state 2. So the area under this line, which is just a rectangle, so it's easier to compute for this process. Now let's try to identify how we can come up with the work done and the heat transfer in the system. So again, we can apply, for a closed system, we can apply our first law of thermodynamics. So E in minus E out is equal to the change in internal or potential or kinetic energy in the system. So we have a work put in, heat will be lost since it is condensed, and all we have here is only the change in internal energy. Okay, you see that these are capital U's, so that would mean that those units would be in SI would be kilojoules, but we want kilojoules per kg, and also we are not given mass in the system. So what I would do is I can just divide by the mass across the left and right hand side, so I can turn these guys into per unit mass. Okay, so small letters now. Okay, so I can compute Q out from here, which would be small w in minus delta U, which is U2 minus U1. Okay. So we can compute the work done since we know the specific volumes, and since it's a constant pressure as well, it would be nothing but P times V2 minus V1, which we computed before. If you do the math, it would be negative 196 kilojoule per kg, and I should probably write this as W out. Okay, and similarly delta U will be U2 minus U1, and you should get that as negative 1743.74 kilojoule per kg. Okay, so then the Q out will be W small w n plus, I would probably want to write a negative, but I can do that, minus delta U. It's the same thing shown here, whereas we want WB in, we got WB out, so we have to change that sign here. So it would be 196 kilojoule per kg plus 1743.7 kilojoule per kg, so we end up with 19.3974 kilojoule per kg. So that's your heat transfer in the process. So you see that the key here, even in all the problems we just did, is to identify the states, utilize the information you're given, and see what all the data you would need, which you can easily find once you know the phase from the tables from the back of the book. Now let's look at another problem where now we will learn how to compute the change in enthalpy based on the process. So you're asked to calculate the change in enthalpy of argon in kilojoule per kg. Again, it's per unit mass basis when it is cooled from 100 degrees Celsius to 25 degrees Celsius. And if neon had to undergone the same process or the same change of temperature, would its enthalpy change have been any different? So first, we know that if it were an ideal gas, the delta H can be computed, and it is Cp times delta T for an ideal gas. The way you can tell whether argon and neon are ideal gases at this condition is you can go to table A1, then you look up argon, for example, and you'd see that the critical temperature here is 151 Kelvin. And the temperature range we are looking at, if you convert this to Kelvin, is about 298 to 373. So we are way above than the T critical. So that would mean that we can consider argon as an ideal gas at this condition. And now let's look at neon. So you can see that even for neon, the T critical is just 44.5 Kelvin. So again, we can safely assume neon to be an ideal gas at these conditions. So now that we know that, it's very easy to compute. Now what you have to do is to find out what would be Cp for argon and neon would be. This you can determine from table A2A. For argon it's 0.5203 kilojoule per kg Kelvin, and similarly for neon it would be 1.0299 kilojoule per kg Kelvin. Okay. So now that we have that piece of information, it's very easy to compute these guys. Okay. So table A to A gives me Cp per argon, which is 0.5203 kilojoule per kg Kelvin, and also for neon I can do that, 1.0299 kilojoule per kg Kelvin. Okay, so I can compute change in enthalpy for argon. If I were to do the math, and it doesn't matter if you convert this to Kelvin because we are taking the difference, so you can just leave it in the same units. So you should end up with negative 39 kilojoule per kg, and for neon you end up with negative 77.2 kilojoule per kg. Okay, now let's look at a process now which is slightly different than what we have been doing. So now we are considering 473. Argon is compressed in a polytropic process with N equals 1.2 from 120 kilopascals and 10 degrees C to 800 kilopascals in a piston cylinder device, and you're asked to determine the work produced and the heat transferred during this compression process. So in any compression process, we always have to put in work, whereas in expansion, it's the other way around. And again, you see that no mass is given, so it would mean that we have to consider everything in per unit basis. That's why your answer should be in kilojoule per kg. So now, before we jump in and do anything, let's quickly see if argon, like in the previous problem, is an ideal gas at the temperature we're given. So if you again go to table A1, like I showed before, the T critical is less than the temperature which we have if you convert into Kelvin, okay, which is 10 degrees C. Or another way to look at is P critical, if it is greater than the range of pressures you're looking at, that would mean that we can consider argon as an ideal gas. So for an ideal gas, from table A to A, for argon, I can determine the gas constant. Okay. I can determine the CV, specific heat at constant volume, and you'll see why I'm gonna do it later in a bit. So now let's write out what we know for the system. Since it's a closed system, ideal gas, let's try to write the first law here. E in minus E out is change in energy in the system based on the internal energy change or potential or kinetic. We don't have potential or kinetic energy change, so all we have is the change in internal energy, and we know that it's an ideal gas, so that makes us our life easier. And if I want to write this as Q put in minus the work delivered equals change in internal energy, and I can do this as a per unit mass. If I divide everything by mass, I want to write this in small letters now, and you see that this is delta U, and for an ideal gas we learned that delta U is nothing but CV times delta T, and let me just write it as T2 minus T1. So you can see that in this equation we can probably quickly find delta U based on the phases here. However, you have two other unknowns here, Q in and work out, so you have to come up with another equation. Luckily, we know that it's polytropic process, so we can go ahead and compute work done, and then we can go back in and substitute the work done and the change in internal energy. We can then determine the Q in. So work done for a polytropic process is P2V2 minus P1V1 over 1 minus n, where n is not equal to 1. Okay. However, in this, we really don't know V2 and V1. Okay. So one way to do this, I know that it's a polytropic process, so PV power n is a constant, or P1 V1 power n is P2 V2 power n. If I do a little bit of algebra, I can come up with P1 over P2 raised to the power 1 over n is equal to V2 over V1. And also for an ideal gas, remember that you can write this PV equals MRT and at state 1. So utilizing this, I can take factor P1 V1 out. So I get P2 V2 over P1 V1 minus 1 divided by 1 minus n. We already know what would be this V2 V1, which is nothing but this. P1 V1 is MR T1. Okay, so I can do that. If you do a little bit of math here, and remember this is big W, and I'll quickly change it to a small w in a bit here. Okay, so okay. So if I take the m to the denominator here, it gives me that the small wb which we need, or P1 over 1 minus n, P2 over P1 raised to the power of n minus 1 over n minus 1. Okay. So what do we know in here? So do we know P2, P1? Yes. We know n, which is given in the problem. We know T1, and remember that you have to use absolute scales here. And we know R, we know N. So we can quickly compute what would be W B. Okay. And I'm sure you guys are good with calculators, so I'll let you guys punch in the numbers, but I can give you the answer. It would be 109.5 kilojoule per kg. Okay. And you will actually get a negative number when you do the calculation. However, I can write the same thing as W in, so if you want to represent it another way, that would be the work put in. Okay, it's just a convention. As long as you know what you're doing in terms of putting work or getting work out of the system, it is fine. And then to compute delta U now, we know CV we know T1, but we really don't know T2 yet. Okay, so we have to find T2. Again, our polytropic process can help us there. So I can write P1 V1 raised to the power n over T1. Okay, if I take the p's from the constant which I had before, I can do this. Okay, if I do a little bit of math here, um, I would get a relation between the temperatures and the pressures at the two states. Okay, and I'll let you explore this. Okay, and this is what you should end up with. So in this, I know n, I know p2, I know p1, I know t1. So t2 you evaluate it to be 388 Kelvin. So now I can go ahead and compute Qin, which would be W out plus CV times T2 minus T1. Okay, so I know W out kilojoule per kg plus CV, the change in the temperatures. So I should get 76.6, which is a negative kilojoule per kg. If you want the sign to look positive, then you can also represent it as Q out. Okay. Okay, so this concludes the session on chapter 4, where we talked about closed systems, how to compute work done, how to evaluate the change in enthalpies for an ideal gas, um, compute the heat transfer, and you also learned why we were so insistent on letting you guys explore the temperature and the pressure tables when we did chapter 3. So that all comes to use when you actually are considering a process. You have to know all of this. Thank you. We'll see you in the next session.